force going back up towards the top. And then in this whole section right here, it was really confusing, but we found out what it was, and Chris will explain that.
Okay, so what
let me ask you a question here. How did you get that spring constant? Did you guys just do a
that was a separate experiment with the force sensor.
Okay.
Yeah. Okay, so what's happening right there is, you probably saw in the video, is that the ball actually dips down. And we were wondering why that was happening, because the buoyant force should bring the ball up. And what we found out was that the ball is spinning really fast right after the spring launches it. And that spinning causes a top spin type effect, which makes it actually dip down. And that's known as the Magnus effect. And it's on Wikipedia. That's the equation right here. Is that cross product between angular velocity and this velocity in the x direction, and then s, which they literally have no information on. It's some constant. So I talked to John, and he gave me something like c1 e to the negative kt, times the velocity. And I had two constants, and as you can imagine, toying with those in Tracker wasn't very fun. That actually ended up not working, so I just kind of went back and did some more Googling, and I found this alternate form on a tennis ball site. So this is for topspin. This is rho, it's the density of water. This is the velocity in the x direction. This is cross-sectional area, and this CL is some crazy constant that they get from differential equations, but basically it's dependent on the angular speed, or how fast this thing is rotating. Okay, so
you're assuming it's rotating at a constant speed?
Yeah, we had to assume that it was at a constant speed because we didn't know how to make that no variable. It was already complex enough. So that's going to make it not perfect, obviously. So first, I'll just show you real quick. From right here, this blue model that you'll see is just when the ball is on the string. And we have the forces are kind of complicated down here, but if you just look in the Fx, there's the spring force, and then there's the drag from the water in the x direction, and in the y there's the gravity.
Could you zoom those? Just click on them, Right?
Yeah, okay. Alright, so the way it was defined is that we wanted this direction here to the left to be positive x, and just the way it's set up in Tracker, it kind of rotates the thing. So up is actually negative y. So as you can see, our buoyant force is going to be up, so it's negative buoyant. And then we have gravity pulling it down towards the positive y, and our drag in the y direction, which isn't very much for this part, is also in that direction. And then there's a period when it comes off. And should I just show the video and then explain this, or?
Yeah.
I'll show the video first. Okay. And yeah. And it gets really slow, so I'm going to stop it and make it skip some frames. Okay. So obviously it's a little off, but if you look at the actual motion of the model, it's pretty similar to the ball. There's some discrepancy of maybe like, I don't know, a centimeter or two, but we have the same arced motion. Okay, so right here is the spring for that teal that I just described. Then this is when the Magnus force really is taking into effect and making it dip down like that. And that one's called spinning. So the only force acting in the x direction now, since the spring is no longer on it, is the drag. And then we have gravity and drag and buoyancy in the y. But we also have this Magnus force, and that's what causes it to dip down. And the reason it's Magnus 2 is because it's with that right side of the equation there, instead of that e to the whatever, which was this one that I ended up not using at all. And this thing right here is that purple equation on the right.
So you use, here, let me make sure. So for the dip, you use, which term did you use?
This one.
That term here, with that CL term is angular velocity dependent.
Yeah, and basically what I did was I looked at the plot of the mass for when I clicked out the points, and I compared it to this, and I changed that value of what I call the M constant until it was as close as I could get. So it ended up being pretty small, 0.034 for that CL constant. And then there's this one, which is, this is really confusing, so I apologize because I can't explain the physics here too well. But this is when it's not really being forced down by magnets anymore. And when I did this originally, the model would shoot way up. It would be rising too fast, it would be moving too fast. And what I figured out was that the drag force needed to be a lot higher, for whatever reason. And I thought about it for a while, and I figured out that the force of the ball moving is not all going into just moving in one direction. Some of it's spinning the ball, so it's moving slower because it's kind of being rotated by the water. It's like if you've ever booted up the computer in there and you see on the main physics site the air that's keeping the globe in one place from the air currents. It's just spinning. Have you guys seen that? Never? It's in like 4C or whatever, that experiment, where they have that really powerful fan at an angle and then an inflatable globe, and it's just spinning, not moving. I think it's kind of the same effect. It's
like a Bernoulli type effect, or pressure difference.
It's not all pushing the ball forward, it's kind of like slipping by and causing it to rotate. And because of the grainy video, we can't tell whether it's rotating or not. So for when it starts rising, I had to throw in an extra constant, which is this yellow part, and I called that rotation. And I multiplied that by the drag and the y, and that made it work really well. I don't know what that is if you guys have ever heard of that force, though. Is there some way to account for that besides just constant guessing? No?
I don't know.
It has to be spinning, I agree, in order for that to happen.
But I'd only really needed it when it was rising. Right
You
here.
could do a test with that to say, you could just put the ball in the water, and you know it's not, just hold the ball in the water and let go of it so you know it's not spinning, and see how much it rises, how fast it rises when you're sure it's not spinning, and see how fast it rises. What's that?
It might still spin though.
Yeah, slightly maybe,
Yeah.
but you could compare this rise rate to that controlled rise rate and see how much different it is. If it's just point, maybe it is just point force, or maybe it's spin, you can see what the difference is. So that'd be a future experiment, right? In your next lab, next time you take 4A, you can do that.
Hopefully there's not next time.
Yeah, well,
hopefully
that
not.
is. Any questions?
Nice job.
Thanks.
I thought that was